Joining us soon is going to be John Stock from the National Innovation Center at the U.S. Geological Survey. In this session, we're going to talk about the vital role of federal science investment in public utilities and maintaining infrastructures in the future. So let's go ahead and do a brief introduction here. Can we see John? How you doing there, sir?
Morning, Nate. Morning, folks.
All right, glad to hear you. We got some audio coming through. So I was thinking real quick before we kind of dive into your background and talk a little bit more about your unique skill set and profession. I'd love to hear just a little bit for our audience. Maybe just explain a little bit about what the U.S. Geological Survey does. And I got to say, like, this photo, it's sentimental for me because this was the last trip I took before COVID. The pandemic was to this really awesome headquarters building. So why don't you tell us a little bit about the U.S. Geological Survey and what makes it so interesting to our people?
Yeah, you went to our Death Star building, which was originally designed as a hospital, which we inherited during the Nixon administration. It is an interesting building. So the survey's been around since 1879. Over the years, of course, we shuffle our deck chairs around with every new administration. But we do four fundamental things, and we've sort of always done them in varying proportions. We map and characterize the nation's lands, waters, and air sometimes, and more recently the ecosystem. So those are the topographic maps that many folks are familiar with, maps of mineral resources, maps of endangered species, maps of geologic hazards, all things that infrastructure industry can use as you think about where you put your assets and how you design them to be resilient against what Mother Nature throws at you. So we've done that since 1879. We also monitor things. And so we have a series of networks for situational awareness. Those include our seismometers that can give us, we're increasingly trying to use them to give earthquake early warning. They can include our surge sensors at the coast for hurricane water levels, our 10,000 stream gauges across the country that warn both for floods and then water as a resource, and a couple of other things I can mention as well. So we map, we monitor, and then we try and forecast. We use those two tools, the mapping and the monitoring, to make models that help people anticipate what's coming at them. And this is really an area where we're, we've always done a bit of it, and we recognize that this is a place we need to improve on, as do many other federal agencies. That's the third thing we do. And then the fourth thing we do, which I sometimes forget, is we try and communicate both to ourselves, which is a surprisingly large challenge, and to others. And that's the place where I often think we do the poorest job, because a lot of our science sort of sits in illuminated manuscripts and doesn't get used in the way that it ought to by folks in industry and in the public in general. And so that's a real challenge area for us.
Yeah, that's fascinating. You know, that's one thing that we hear from our customers all the time, is just the challenges of communication, keeping the same story, the same kind of a thread of communication across all the different teams. That's something that I know the pains of the people here in the audience can really feel. So thank you for that introduction on the U.S. Geological Survey. Next, let's do a little introduction, a little bit more about your background and what makes you such a great speaker for this session today. Yeah, exactly. This is where we get to celebrate you a little bit, John. So don't be too uncomfortable. So John has founded and runs the USGS's National Innovation Center, whose mission is to identify, pursue, and develop national scientific challenges, as John just alluded. His expertise, John owns more degrees than my team owns Trimble devices. So this is, you are eminently qualified for our next panel here, and I'm excited to dive in a little bit deeper. So maybe we could just kind of start off in general. Your mission of identifying, pursuing national scientific challenges, how does your group, the National Innovation Center, specifically help with that?
Well, so it's interesting. I was listening to your last panel, and the last panelist, or the next to last panelist, was saying that you shouldn't just go out and jump on technology. You should figure out how it serves you. And so we have the same sort of notion, which is we look for big national problems where there's an observation gap, right? And so examples of those could be that our great stream gauging system, it's 10,000 real-time observations of water, but it occupies a tiny fraction of the actual water out there, right? So there's an observation gap. Many folks would like to know what the stream in the back 40 of their property is doing, or real-time flood inundation alerts for areas beyond the stream gauges. So we look for observation gaps like that that matter to people and that matter to both industry and the public. And then we think about the palette of technologies that are out there that would fill that observation gap, right? And so that, in the case of the stream gauging one, we're exploring this new technology for telemetry and sensors called LoRa, long range. It's cheaper, it's low power, which means we need to service it less often, and it can have a smaller footprint without a solar panel. And then, of course, the other big issue there is how do we get it safely back into people's hands, the communication part. And so there we're exploring different ways to do that. So we arrive at our sort of funding priorities by thinking about big national challenges and then looking at the palette of technologies out there. And we always partner with either industry or other federal agencies or academia to go after that technology, because we're great subject matter experts on water or earthquakes or volcanoes, but we don't we don't hire large cadres of engineers. And so that way we're flexible in terms of how we can look at the technology space, and we can pick partners to go after a particular technology, and with the understanding at the end of the day, we expect that partnership to result in sort of either a new industry, well, not a new industry, but a new company, or sometimes sometimes a new industry. So that's how we try and get there.
Got it. In our last session, one of the panelists' comments that I really appreciated was the need for just not only trust in general, but also just being able to understand your people and aligning values to the solutions that you're rolling out. You talked a little bit about partnerships. Could you tell me a little bit about some of the values that you seek in the partners that the NIC works with, whether it's private institutions or academic?
Right. Well, yeah. Trust is the most valuable thing, right? And of course, it's the thing in the shortest supply these days. Like you've all read the polls about where trust is these days, and there's not a lot of it out there. That's pretty vital for us because ultimately, partnerships don't work unless you have trust, right? And so when we're thinking about how to partner with industry, the very first thing we do is we assume that industry's got to make a living. So we try and find an alignment where the thing we want to do is aligned with the thing they want to do, or as I call it, a common destination. We want to go someplace together. So first, if you have a common destination, you have this trust that you're both going to the same place. If you're going to different destinations and someone's always trying to grab the wheel, right? I'm sorry to be so blunt about that, but it's true. And so identifying a common destination is I think, is one of the foundations of successful partnerships. That means being pretty blunt up front about like where you want to go. There's a certain amount of flexibility, like, I could take the second stop or the first stop off the bus, but I want to get to the same place. So we look for an alignment where we want to get to roughly the same place as our technology partner. We're realistic about the fact that they have certain constraints that we don't have, and vice versa sometimes. And we try and create the partnership in such a way that industry or an academic partner or another federal agency can play to its strengths and we can play to ours. That's also called roles and responsibilities, which I'm sure many of your audience think a lot about, because in any organization, you need to at least have some fairly decent guidelines about those, or things get really interesting. Did that answer the question, Nate? I wasn't sure.
It did. No, that was a great background there, and I appreciate that. Trust is going to be continuing something that we talk about, and I appreciate the conversation on bluntness. So if any of the questions I ask you over the next 20 minutes suck, just say it, and we'll move right on. All right.
All right.
So let's hop into the first one, which is I'd really be interested to hear from you what you think some of the biggest challenges facing our national infrastructure are in the next decade or two, or whatever time frame you'd like to look at them in.
Well, I think there's two that sort of spring to my mind, and we've talked about them a little bit before. One is the challenge of essentially leveraging all this new technology in a way that doesn't break your budget, or in other words, how do you reduce your operations and maintenance costs using new technology rather than drive it sky high, right? So that's the problem of how do you harness what you know is out there to serve your needs. So that's actually a huge challenge, as I'm sure your audience knows better than I do. The other broad challenge, I think, is and I find this every day, which is, I have a lot of great opportunities staring me at the face, but how to essentially get them from sort of research or low technical readiness levels into something that's actually usable in an operational mode. That's a huge challenge too, particularly in the current funding environment. We're pretty sparsely funded, so we we work hard at using the scarce dollars we have to do things. And obviously there's some more discrete examples of those challenges we could use, but I think those two broad challenges for the infrastructure industry, how do you, the digital wave is your feet are already wet, but how do you pick out the things that are actually useful to you, and don't just simply destroy your budget? And then two, how do you get from a trial implementation of those into full-scale operations? And those are old problems. They've been around for a long time, but they remain like enduring problems, I think, enduring challenges.
I see. Thank you. No, that's a great segue. One of the things that's been very clear in just reading up on the National Innovation Center, we've heard it even in our last panel, is just the impact of natural disasters that are impacting all of us. Anybody who's putting a truck out into the field knows that things can shift in a moment's notice. And your department is actually working on some really interesting things. And I've seen something here that makes me really excited as a geospatial technologist, which is the ability to detect millimeter scale change in our land.
Yeah.
And I'm curious if you could bring up tell the audience, why is that important? Why do we need millimeter level accuracy? And what will that allow us to do?
Right. So your audience may already be familiar with some of the aspects of this, but over the past decade and a half, what space agencies, along with a bunch of really smart geodesists, have shown is that you can measure changes in surfaces at a fraction of a radar wavelength, which turns out to be millimeters, right, from space. That's a pretty amazing thing. And in essence, it means that if you put an interferometric synthetic aperture radar, that's a fancy term for it, but it's called INSAR for short. If you put it in orbit around the globe, you can essentially over time measure very subtle changes in the surfaces that you're looking at, because you're looking at changes in the radar wavelength that comes back to you. So you get a peak when it comes back the first time, then you circle around the Earth and the surface reflector falls a couple millimeters. Now you get a trough in the radar wavelength. So to get to that offset takes a lot of calculation, calibration, and other things, but folks have shown it can be done. And the implication then is that you could have a system of satellites around the globe, and you could essentially detect over wavelengths, spatial scales as small as 5 to 10 meters, changes in the elevation of things down to sort of millimeters. That potentially is pretty transformative. So let me just give you one example that my friend James Grabe from Federal Highways, we walked through with him. So Federal Highways, of course, has this huge network that they work cooperatively with the states to maintain. They spend somewhere north of $200 million in finding problems on that highway, right? So what this technology offers, in essence, is that every week or a couple weeks, when you get a new radar seen from orbit, and it can be shorter if you want it to be, but at least that's where it is now, you could essentially use AI to interrogate that scene and ask, where in my federal highway network do I see non-noisy pixels that tell me I went beyond my elevation change tolerance, right? So by hitting a button, you can essentially flag all your O&M problems from a national network that usually consumes several $100 million to find those problems. That means you can take that money, and instead of using it to find the problems, you can use it to fix the problems. That's a very appealing idea for infrastructure operators, because again, that's reducing your O&M of finding the problems. PG&E would feel the same way, I suspect. Well, I've talked to them about their power towers. Be great to know if one of them is leaning one way or the other, or in particular if they got vegetation encroachment, which one can also detect using this kind of technology. So that's the sort of reducing the O&M part. I can talk about a few other aspects of this for coastal design that people, it's fairly obvious to people that the sea level is rising, but the rate at which it's rising is, globally around a couple millimeters, plus or minus some. Turns out the land is actually sinking way faster than that in some places. So anyone who's lived in Houston, or near Hampton Roads in Virginia, knows that the land is actually sunk in those places because of groundwater extraction as well as a few other things way faster than sea level rise. So being able to have a picture of where the earth is sinking and where it's rising means that when you design your coastal infrastructure for resilience, you're designing it for the right rate, not the one you think is happening. And your audience will know how much money goes into coastal infrastructure, but it's many billions of dollars. So do you want to build that once or twice or 3 times? You can build it once if you get the number right. And so this technology means that not only can we save on O&M for infrastructure, but we can also design our infrastructure to meet what's actually going to happen. And of course, that ultimately, that's the whole point of infrastructure, is it's the roof over your head when it rains. It's the thing that allows you to do things that you couldn't do when Mother Nature gets upset with you.
Thank you so much for that. So tell me a little bit, like, how far out is this great kind of future you're talking about that we'll be able to start integrating this data into our own models and into maps as geospatial professionals?
Right, this is a great data layer for you guys, right? Because you're one of the companies, and there are other companies too, that can turn this into value, right? If you just bring back a big map of pixels, there's no value to you. But once you can do that targeting, then you got value. You've created value. So that there's a current, and some of your listeners will know, there's a current network of satellites that are operated by the Europeans and the Japanese that do this at a much lower resolution and with less capability. And so you can do a 90-meter pixel approach to it now that, and I think the repeat times are sort of 3 to 4 weeks or something like this. And unfortunately, the wavelengths those radars are operating at, you lose a lot of the signal because of vegetation. So 2023 is when NASA intends to launch its partnership with the Indian Space Agency, which they're calling NISAR, and that's this next generation radar satellite that will do what I just said. So 2023, I will say that we're submitting this. USGS doesn't have the funding to make the land level change map we're talking about. So we are actively looking to spread the message to folks who could be users to inform them, like here's the value if the nation decides to do this. And so that 2023 is when the satellite would make it possible. But obviously we're going to need a small investment, somewhere around $5 to $6 million a year in order to make the map, and that's what we're still looking for.
Gotcha. No, that's great to hear. Just some background on Unearth. We actually started with geospatial change detection for construction companies doing landmass extraction. And when I read in some of the materials that you shared over the millimeter scale accuracy, it blew my mind. Because, like, for one thing, like, you government folks have all the fun toys. You guys have all the good tech.
I deny that. Industry and DoD do, but fine.
Well, I'll say your feeds from the satellites look a little bit different than mine. I'll say that much. And so I think it's really fascinating just to hear that just within a couple of years, we're going to be able to detect change on scale.
Yeah, I want to make clear that this is not going to obviate the need for the kind of structure for motion UAS work that a lot of folks do, because when you're digging, you're changing the reflector. So you can't use this technology to do what you just talked about, right? So we don't see it as basic. We don't see it as disrupting that industry, because that industry is going to survive and do very well. The use of UAS and other sort of remote platforms to automatically capture, how the project is going. That seems like a very strong market to me. And obviously, you're going to need a company like yours to turn that into business intelligence. But this will create new markets, I think, because it's going to point companies in the direction of A, how do we extract the signal from this huge map? And then B, it's going to focus people on places they weren't focused on before to go in and do more detailed surveys with all the sort of suites of tools that you all use. So we see it launching a lot of industry rather than destroying industry.
I see. That's an exciting point. And I want to get back to the topic of UAS and drones in general. But before, I want to talk about what I believe that the great innovation here you're talking about is going to allow us to better predict floods and natural events. Is that correct? Because one of the things that we've heard is that, if sea or elevation tables are rising on water, I might have sent a truck there this morning, and if I knew 10 hours before that this area had been flooded, I could save myself $3,000 to $5,000 per truck that's going out there. Is
Right.
that something? Is that a viable technology that's coming down that will be able to predict floods and predict at a high degree of certainty what's going to happen the next day?
Well, we can predict floods now if you've got 3 days of good forecast warning, right? So we can, and our partners at NOAA do a great job of that, because we can look at the rainfalls that are coming and compare them to past rainfalls and make estimates of, yes, there's going to be a flood. We're less good at telling folks exactly where the flood's going to be, and no one's very good at telling people many days in advance of where the flood will be. That's a staggeringly difficult problem, but it gets back to that point about, like, okay, what's the observation gap and what technology illuminates that gap. And so in this case, some of the work we've been doing is we've been asking the question, your listeners will be familiar with companies like Planet, and there's a few more coming out that provide daily imagery and sometimes imagery at sub-daily time steps. And so one of the questions we asked is, that's a classic example of like a huge amount of data raining on your head, and no single person has the time to turn that into intelligence, right? So that's where machine learning comes in. That's where you sort of encode a set of algorithms that capture some element of what a human would do, and it's always some element. It's never quite as good, but because humans don't have the time to sort through the entire planet every day, it's a useful tool. So we asked the question in partnership with NASA, can we take that imagery and automatically extract where water is on it? Because if we could do that, then we'd at least have a lower latency map of where the water is. And if we did that through time, we could essentially create maps of places that get inundated for a particular kind of rainfall. That would actually help us with the problem you were articulating, which is, if I've got a 3-day forecast, which areas are going to flood? At that point, then we can look at the historical precedent, look at which areas get inundated on the landscape for that kind of rainfall, and then use those statistical relations to make the map you just described, the inundation map, that's 3 days heads up. That would be a real value saver, because now you can anticipate what's coming at you and move to meet it, as opposed to reacting.
Thanks. No, thanks for helping us understand that. Along a similar topic, one of vegetation management is top of mind for many people in the utilities industry. Do you see any way that your team can help us improve how we monitor electric transmission lines for vegetative hazards or other critical infrastructure?
Yeah, well, obviously that's a great concern to anyone who's, and those of us who've been in California have watched as PG&E has been forced to essentially cut power to some lines, because there's even with their efforts at management, there's so much there's so many unplanned things out there that can take out your power line, right, without your knowing it. So one of the options that PG&E uses, and other companies use it too, is sort of annual LiDAR surveys. So you survey your power lines, then you get a company to take all those the points that come out of that survey, these point clouds from LiDAR returns, and classify them, and then you prioritize your sort of vegetation management using that, and that's a great tool. The challenges to that tool, of course, are that it happens once a year, because usually it's expensive to fly LiDAR. It's a budget buster to fly it like every week, not to mention the time you got to spend and the money you got to spend getting that data turned into intelligence. So one interesting possibility there is that the same sort of radar technology we're talking about could be used to improve our sense of which parts of the infrastructure are susceptible either to movement via geologic hazard, whether it's a landslide taking out your power tower or some other thing. But then B, also, it could be that we can turn some of those sort of weekly radar takes from orbit into intelligence about where vegetation is encroaching on your power line in such a way that you could then prioritize management at weekly scales rather than at annual scales. I think it remains to be seen whether there's a value add to that. But everyone I know would love to be able to have a weekly sit rep on a pulse on their infrastructure, and it's so hard to do that when you've got these massive infrastructure lines that are going across places with geologic hazards, ecosystem hazards from falling branches and things like this. So radar offers one option to that. I think there are others, but that's one that, again, with the National Land Level Change Map, we're looking at trying to do that.
I see. No, that's great. You talked a lot about the present and monitoring and the need to monitor and map what's going on there. I'd like to focus a little bit more on mapping and dive in a little bit deeper here. And specifically, I'm curious, a question for you. You know, how can historical maps help us better predict resources and hazards of the future?
Yeah, I mean, I, so I've got map drawers full of dusty old maps because I love maps, right? And everyone's like, why are you keeping those things? Well, all right, so they're pretty for one thing. But another thing we've discovered is that, you know, with every technological advance, sometimes there's people who want to throw away what you had before because they think somehow it's no longer worthwhile. But actually, the real power comes from making the two work together. And so one of the things we've realized is that we have very detailed maps, for instance, of places in the nation. And those detailed maps are when a gal or a guy sat down and penciled in, usually from low altitude air photos, either geologic hazards like maybe faults or landslides, or maybe it was the distribution of rock and soil at Earth's surface, right? And so each of those maps, those old maps, is essentially a training data set in this sense. You could take, you know, daily planet imagery or you know, digital globes, sub-meter imagery from orbit. You could lay it over a place like that, and then you could ask the question, can we train our algorithms to replicate what the gal or guy did? Because the gal or guy is always going to be a better mapper than the algorithm, sorry. But they can't do it at scale. So then the question is, if you can train the algorithm how to get 90% of the way there, then you can apply it at scale. So we looked at one problem where I always thought that we had pretty good maps of what parts of California were rock and which ones were soil. That seemed like really straightforward, right? Why would we not have that? So when we compared some of those older maps I was telling you about to the sort of existing national land cover maps that are based on our Landsat data, as well as the Soil Conservation Service or NRCS maps, we found that you know, the coarser NRCS and Landsat maps were wrong in some cases by a half, right? So think about that. You're using a map that's half wrong. That's not great. So then we asked, all right, how do we not spend a lot of money and a lot of people hours and at the same time learn from that small map where we, you know, really did it well? And machine learning is a great tool to do that. So now we're essentially in the process of taking the Sierra Nevada and taking some of those older maps I was telling you about and using them to train machine learning algorithms to extract soil versus rock from digital globe imagery. And we do a pretty good job at it, right? So that's a great example of how you marry old with new. You take your the thing that your gal or guy did because they had a tremendous amount of skill, and you train the algorithm on that, and then you unleash the algorithm with high performance computing and digital imagery across a broader area. So that model, I suspect, can work for a number of different applications within infrastructure as well as, you know, the broader science community.
Fantastic. And along the lines of the great work that you're doing, how can people in the utilities industry, technologists like myself and my colleagues here at Unearth, how can we help you in your work and participate in research and add to your mission?
Well, so I'll just say that we always like to find common destinations to go to with you all because you guys are really good at leveraging new technology efficiently to do things really quickly at scale, right? And those are all places where federal agencies have underinvested, and you can debate why, but we simply are. And so the example I was just giving of like, yes, we can train it to do this on the Sierras, but what if you then told us, hey, we'd like to do that across the nation? We would just throw up our hands in despair, right? Whereas a company like yours or some of the other companies out there would have a real sense of how to take that problem to scale, right? So one part is we like partnerships with you all where we're doing this sort of, you know, we're building the foundation to show you guys that yes, we're buying down the risk. This is a low risk proposition, and then you guys see how this basically becomes, you know, you see a business model, and then the partnership thrives because we want to get to the same destination, like this map for the country that improves our, you know, either our mapping of resources or our mapping of hazards. So we love those kind of partnerships, getting to a common destination, because in almost every case I can think of, industry is really good at optimizing workflows in a way that I don't think our federal community is.
Fantastic. All right. I'll take one question from the audience here, which is a good one. So, John, this should be an easy one for you. You're no stranger to the rodeo of innovation and bringing change. I'm curious if what are some of the best practices you've adopted for rolling out and implementing new technologies?
Oh man, right. This is the you want a doctor that's killed a few patients to operate on you because they've done it wrong. They know how to do it right now, right? That's that question. Uh, Best practices for, I think the same practices we talked about earlier for partnerships apply here. Is you want to make sure you're going to the same place, and there's always that element of chemistry between your people that matters, and that's never an easy. There's no cookbook solution for that, right? So part of the challenge of leading any innovation partnership is also solving the human chemistry challenge, which is getting the right people. And sometimes you have to move people around until you get it right. So common destination, getting the right chemistry between the people, which is and part of that is telling your own people, setting some expectations, right? Because classic science, a lot of my scientists are like, engineering is not brain work. All they just go to a table and look it all up. Why are they taking so long to get back to us? Then I have to explain to them that actually engineering requires all the things that science does plus more, because you've got to be intuitive but mechanical and calculational, and you've got to be creative to do good engineering. And so getting both sides to recognize the strengths in the other party, and then making them feel like they've got a strong role and responsibility in the project, right? So common destination and human chemistry.
John, thank you so much for a great answer, really highlighting some of the things that we've heard and adding a new spin for that. I'm looking forward to talking and learning more about some of the work that you guys are doing and more partnerships in the future. So thank you so much for being our guest today, John.
My pleasure, Nate. Thanks for the great questions. And I'll just say to your audience, if folks want to reach out, we're always happy for partnerships. And as I said, we're trying to build a constituency of folks for the National Land Level Change Map. We just put in a request, or will be putting in a request to the presidential transition team for this as a topic. So,
Okay. We're rooting
stay
for
healthy,
you.
everybody. Okay, signing off. Bye.